of these chapters. And I'm going to be working off of a PowerPoint as opposed to a PDF, but if you want to follow along with me, these are the files that you can download. And let me switch over to those, and then we can get this show on the road. Okay, so if you had first semester with me, or if you just used the same textbook for first semester, we didn't really do a lot of jumping around in that set of chapters. That sequence was kind of laid out just the same way that our labs are, but we're going to jump around a little bit in this semester. So we're going to start with chapter 16. I think it's 16 and then 17, and then we're going to go to 33 and 34 because those all used to be they used to be in a line beforehand, but the 4th edition really kind of mixed some things up. So let me start sharing our PowerPoint here. That again? Okay, so this is the first of 2 parts. I believe all of the chapters that we're going to cover in second semester are going to be broken into 2 parts like this. And the first thing that we are going to encounter, or that we have to kind of think back to, is the concept of a model. We encountered a handful of them in semester 1. I think the very first day of our lecture, we would have run into the term particle model. If you remember when we were learning how to make motion diagrams, and then ultimately we learned how to augment those and to turn them into free body diagrams once we got some more knowledge about force. But the point there is that the particle model is something that we can apply to kinematics and dynamics. So how an object is moving, and then the why, the description of why it moves the way that it does. When we ran into a discussion of rotation, we found that the particle model failed because the particle model ignores the size and shape of an object, and that is relevant when we're talking about rotation about an axis. If I had, like, for example, this pencil, and I wanted to rotate it about its center of mass, the amount of force it would take to achieve a certain angular acceleration would be different than if I were to rotate it about a different axis. So shape matters when we're talking about rotation. So the particle model is not enough anymore. I don't recall whether we used, or whether I used, the term thermodynamic energy model when we were in the 4th unit of semester 1, when we were learning about like the difference between a translational kinetic energy and a like a microscopic kinetic energy, or when we were talking about the ideal gas law and the first law of thermodynamics. But that in and of itself was a model as well. When we were discussing ideal gases, we were using the framework that the gases that we were talking about could be modeled as individual particles that were capable of undergoing collisions with each other and with the walls of any container that they might be in. They had all kinetic energy and no potential energy. That was that's what's implied by an ideal gas. And now we're developing another model, a wave model. And what we are going to apply this to first is the concept of a traveling wave. This is the type that is kind of easy to visualize if you imagine a wave that's propagating down a string. Or even if you were to imagine standing on a beach and looking at a water wave that was moving toward the shore. Water waves are a bit more complicated than a wave on a string, but those are both examples of traveling waves. So there's some sort of disturbance that is not fully disorganized. There's some rhyme and reason to it, and it travels with a well-defined speed. And we're going to talk about waves on a string and waves on a spring more than we ever talk about water waves in this discussion. There is a brief description of fluid dynamics in our textbook if it's something that you are kind of interested in. So like the concept of buoyant forces and things like that. You have to incorporate some of that to like fully get a grasp for how a water wave works, but we can still understand how waves work in general if we split them up into these two kind of basic, simple ideas. So let's imagine that we've got a wave on a string. Let's say that one end of this string is connected to a wall or doorknob or anything that's fixed. If you were responsible for producing some sort of disturbance on that string, then in order to get that disturbance to move away from you, you would want to move your hand up and down. And I want to point out here that you could also cause a wave pulse to propagate if you moved your hand like left and right. That's a little bit harder to visualize or to see what I'm doing here with my little webcam, but it's a little more straightforward, or I guess it's more obvious if we think about wiggling the string up and down so that we can make a pulse that travels left to right. So this would be an example of a transverse wave because the direction of the wave propagation is perpendicular to the direction that you would have to move your hand. And not to harp on it too long, but if you were to imagine taking a string just like this one, and instead of moving your hand up and down, you did move it back and forth, that displacement that your hand is causing the string to undergo would still be perpendicular to the direction of the motion. It would be like looking at, we do like this maybe. If I'm moving my hands up and down and my wave is propagating toward my webcam, if I were to move my hand this way, my finger and then the palm of my hand are still perpendicular to one another. So those would just be two different looking transverse waves, but they would both propagate away from the point where your hand makes contact with the rope. Next, if we were to switch out our string with a spring, then we could imagine, and just to make it as simple as possible, let's say that the spring is sitting, let's say on the floor, you're in a hallway somewhere, and one end is fixed, just like we saw with the string previously, and then the other is moved back and forth. So your hand moves one end of the spring back and forth. What you are doing now is generating a wave pulse that is it doesn't differ in terms of height, like the one that we see up in the transverse example does. It differs in terms of compression. So just to take a quicker or a closer look at what's going on with this spring here at the bottom, we have these black dots that represent like consistent spacing. Imagine that that spring is just at rest. It's neither stretched nor compressed. If you could take a Sharpie and then draw a dot every 3 coils, is what it looks like we have here, then when it's at rest, adjacent dots are always going to be the same distance away from one another. However, once you start generating this wave, what you would observe if you could take a snapshot is that in some places on the spring, the dots are closer together than they were when the spring was at rest. At other places, the dots are farther apart than they were when the spring was at rest. And then you'll find sections of the spring where the spacing between the dots is exactly the same as what you would have seen when the spring was at rest. So in other words, you have to generate a disturbance that changes the elastic potential energy of any one of these little segments or these little intervals, maybe. So to say that another way, if we look at these segments that are on the right-hand side of this little compression, they are neither stretched out nor compressed. So there's no elastic potential energy stored in that section of the spring. And if I look at these two segments that are on the left-hand side, closest to the hand that's doing the generating, they're also neither stretched nor compressed. So there's no potential energy there either. But when we look at these segments in the middle, we have one that's stretched out further than beyond the equilibrium spacing of the the coils in the spring. And you've got another section that is compressed so that the equilibrium spacing is bigger than what we see here. So both of those sections of the spring have some elastic potential energy. And since the disturbance is moving through the spring is not flying out of your hand the same way that the string in the original or the transverse wave is not propagating left to right. The disturbance is all that's propagating. So you can think of this section of the spring that's on the far end as the part that's waiting for the disturbance to get to it. The sections that are closest to the hand are the ones that have already allowed the disturbance to go through and they've already gone back to equilibrium. And then you've got this compressed section and this extended section, where the compressed section is where the pulse is now, and this extended section is where the pulse was a moment ago. So in other words, that section of the spring is still on its way to going back to equilibrium. It's just not there yet. So as we saw in that previous slide, we can sort waves into either longitudinal or transverse based on what you have to do to generate them. There's another way that we can categorize waves based on what, if anything, they are traveling through. So both of the waves that we saw in the previous slide are example of mechanical waves because they have to go through some material medium. I have to have a string or a spring in order to capture that type of wave. If I just move my hand up and down or back and forth without touching some sort of medium, I'm not going to be able to generate a compression and an extension for the spring, or I'm not going to be able to change the gravitational potential energy of different segments of the string that I saw with the transverse case. That is, we can break down the energy that's going through this rope the same way that we did with the spring. Instead of elastic potential energy up here, it would be gravitational potential. An electromagnetic wave can travel through a medium, but it doesn't have to. And this is exactly what happens when you see, let's say, a light wave travel through, let's say, a window. Let's say sunlight comes from outside into your room. That sunlight is traveling first across the vacuum of space to make it to Earth. Then it's moving toward or through Earth's atmosphere. It's going to move through glass. And all three of those segments, so vacuum, atmosphere, and glass, they all represent materials or media that have different indices of refraction. We're going to talk about that a little bit later on, but you can, for the time being, just take that as an acknowledgement of the fact that this one light wave is not traveling at the same speed through the vacuum as it will through the atmosphere or through the glass. The speed of that wave is changing. The point is that the electromagnetic wave is something that we can tie back to the oscillations of an electromagnetic wave. So in other words, this is something that we're going to delve very deeply into when we get to our middle two units that talk about electric fields and magnetic fields. They're self-sustaining in that they don't require, if we think back to the example with the person holding on to a string like this, if this person just moves their hand up and down once, they're going to make one pulse like this and that's it. So in order to generate a consistent wave, they would have to consistently move their hand up and down. That's different for an electromagnetic wave. Once that electromagnetic wave is produced, it doesn't have to be continually generated, if that makes sense. It can sustain itself and just travel either through a vacuum or across a vacuum or through materials that are at least partially transparent. Then matter waves, we're really not going to be able to do anything with these until we get to Unit 4. These are related to the concept of modern physics and like quantization. So we're all pretty familiar with the idea that light can be modeled as a wave and as a particle. So how do I want to phrase this? If a particle can have, or if a wave can have particulate-like behavior, can we run that the opposite direction? Do particles have some sort of wave-like characteristic? And the short answer to that is yes. And something, kind of food for thought to kind of think about until we get to our fourth unit. Any material that's made up of matter has an associated wavelength. That's true for each one of us. It's true for the apple I've got sitting here near my computer. It's not a wavelength that we interact with the same way that we interact with like visible light or even types of electromagnetic radiation that our eyes don't pick up. But there is an associated wave-like behavior with matter. So this is not just it's not just a weird property of light. It's something that we can find in all types of matter. But like I mentioned, we have to kind of get our field theory under our feet before we can approach these matter waves. So we're going to shift back to the first item in that list, mechanical waves. That's what we're going to spend the bulk of this chapter talking about. We are going to talk a little bit about electromagnetic waves, but they're going to come back, or they're going to recur over really all 4 units of the course that we talk about. So when we were thinking about we were kind of thinking through the wave on a string and the wave on a spring, the way that we knew that there was some sort of pulse traveling through either one of those is because some portion of the medium changed. For the string, some portion of the string was pulled up above what its equilibrium position was. And for the spring, the coils were either closer together or further apart. So there was a disturbance that was going through the material itself. The string and the spring were not actually moving through space. And that's part of, kind of gets to the heart of why we need to develop a new model for waves. Because if you just imagine the string, let's say that you are moving your hand up and down, you are causing a disturbance that is moving along the string, but the string itself is not moving through space. So we can think of a medium that has some sort of disturbance going through it in terms of, let me phrase it this way. If we wanted to write a displacement function for the rope, it would matter, let's say, where your hand was vertically at any point in time, and it would matter when your hand was where it was. So that's a real clunky way of saying that this wave model has to be able to accommodate temporal changes and spatial ones at the same time. And we didn't ask the particle model to do that, and we didn't ask the thermodynamic model or the rigid body model to do that. So that's why we have to develop something new in order to understand how waves work. What we're going to start off with are mechanical waves that travel with a fixed speed. So if you think back to that example about a light wave traversing through space, moving through our atmosphere, and then moving through glass, we would just look at one of those media because the speed would change as it crossed from one medium to the next. So if we think about like a wave on a string, the only thing that could affect the speed of that wave is if we change the properties of the string somehow. So if the string started to fray, or if we connected that string to one that had a different linear density that we're going to talk about coming up, then we could change the speed of the wave. Maybe counterintuitively, the speed at which you move your hand up and down doesn't dictate how quickly the wave itself propagates away from you. So that speed at which the wave propagates away from you, this depends on the properties of the medium. And there has to be some sort of elasticity to the medium. And elasticity is something that we talked about in semester 1 when we were encountering like potential energy, elastic potential energy in particular. So if you had, instead of like I'll just demonstrate with this pencil again, imagine that I can connect one end of the pencil to my wall and I move the opposite end up and down. this material is not elastic enough to actually give rise to a wave. All the pencil is doing is kind of sweeping out an angle over some amount of time. So I could figure out like the frequency that my hand is moving up and down, but this can't produce a wave because it lacks the elasticity. So for a mechanical wave, the easiest one to visualize is the wave on a string, the one that we started off with. I mentioned that a water wave is a little bit more complex. That's because it's kind of like a not a cross section, but like a combination of a transverse wave that behaves like one on a string and a longitudinal wave that behaves like one on a spring. So in other words, the fact that water is not rigid means that there's some compression and expansion in addition to the transverse portion of that wave. So that's why those are a little bit complicated. And sound waves can be modeled just like the waves on a spring. Instead of coils of a spring getting closer together and farther apart, the pressure in the inner room. So if you think about what's going on right now, I'm talking to a microphone. That microphone is turning that signal into something that it can transmit to you, and your computer can interpret it as a sound wave. But within my room, this half of it, I'm setting up a pressure wave so that the pressure of the air in the room is changing as a function of time. I'm sitting in the same place, but the sound that I'm producing is making it to my microphone without the benefit of a giant spring that's connected to my throat. So a sound wave works just like a wave on a spring. It just replaces the coils of a spring for the particles of air that make up the air in this room right now, and the room that you're in too as well. Okay, so we're still talking about mechanical waves. We're going to start with transverse waves. So the string that's connected to something, and you move your hand up and down quickly. Let's imagine that if you could measure the equilibrium position of this string before you start wiggling it, and you are careful just to move your hand up and down. You're not going below where it was previously. You're just going up and then back to the equilibrium position. You would end up with a pulse that is shaped like this one here. There's no part of the string that's going below your equilibrium position, but we could figure out, or we could directly measure the width of this pulse, and we could time how long it takes for that pulse to go from one end of the string to the next, provided you had a timing device, and let's say that you were allowed to measure your string. So that speed has got to be the same as what's represented by this green velocity vector here. But we can determine what that speed should be without needing to know how long the string is, and specifically without needing to know how much time it takes for the pulse to go from one place to the next. If we use this expression here, where this is going to be the speed of a wave on a string specifically, this will depend on two things: the tension in the string and then the linear density. This is mu. And when we encountered linear density in semester 1, we were using it as a coefficient of friction. It was a mu with a little subscript, either a K, an S, or an R. Without a subscript, that's going to be our key that we're talking about, a mass to length ratio. So these units don't break down any more nicely than just kilograms per meter. It's telling us how much mass is contained within some unit length of this string. T sub S here, this is going to be the magnitude of the tension vector that we can draw acting along this string. There's an S subscript here because we are also going to talk about the period of a wave. So the reciprocal of its frequency, in other words. So we have to have some way to tell the difference between capital T, that means period, and capital T, that means the magnitude of a tension vector. So T sub S is always going to be a string tension. It's not immediately obvious when you take a look at this, but the units of T sub S will be newtons because it's a force. We know that the linear density is going to be kilograms per meter. So when you take that ratio and take a square root, you will end up with meters over seconds, so that you are predicting the speed of a wave on this particular string. So with this particular linear density and this tension. And it's not too difficult to think about how you could change the wave speed for a string that has some given linear density mu. I believe, yeah, that's what our next thought question, or our first thought question, is going to pose. So our goal for this thought question is to make our wave travel faster. And we've got our two formulas here for reference. We could increase the speed of a wave on this string by using a longer string of the same thickness, density, and tension, using a heavier string in terms of mass. So it's got the same length, but the tension's the same. Use a lighter or less massive string that has the same length and the same tension. You can move your hand up and down more quickly, or you can move your hand up and down a larger distance. Take a second to see if you can determine which one of these choices would, or which one of these options would result in a wave speed that's increased compared to ones that would either cause a decrease or no change at all. So take a second, we'll talk it out in a moment. Okay, so let's see. Got a guess here for C. That is correct. Do you want to explain how you came to that conclusion? I can kind of start you off. D. Oh, thank you. That's okay. All right. So your intuition was correct. So D and E, neither one of these would change the wave speed because neither one of them changes the linear density or the tension. So it's not too difficult to imagine what would change if you were wiggling a string up and down like this and you just moved your hand either a greater distance or you just went faster. The look of the wave would change, but I suppose the shape is probably a better term, but the shape of the wave that you observe is directly dependent on how you're moving your hand. So there's not one way that you could change like the range or the speed of your hand without changing the shape of the wave. So D and E wouldn't actually result in any change in the wave speed. A longer string of the same thickness, density, and tension, a longer string with the same thickness, if we take a look at our linear density here, this would cause your linear density to get larger. So that down here at the bottom, that means that your wave speed would get smaller ultimately. If you used a heavier string of the same length, that would have exactly the same results as what we saw in case A. So it's case C that would cause the linear density to, that would cause, the tension would stay the same. But if you had a lighter string of the same length, this is going to cause your linear density to get smaller. And since it's in the denominator, that would result in a greater wave speed. Okay, we've got an example question to work out. I'm gonna jump over to OneNote for this. So I actually have to log in to WebEx again. I haven't done that yet. But while that's going, let's take a look at this example. So a 3.7 meter string with a mass of 5.0 grams is fastened to a wall at one end, stretched horizontally to a pulley 3.0 meters away, then connected to a hooked 500-gram mass. If the string is plucked near the wall, how long will it take for the resulting wave pulse to reach the pulley? So let me stop sharing here. I'm going to log in on my tablet. What my information is. 180-970-6. Okay. Let's start sharing here. OneNote. Okay, here is our practice problem. So let's draw a picture of this just to get started. So we have essentially this situation. Imagine you've got a tabletop like this. You have pulley. We know that this hooked mass is 500 grams. And let's let this left edge be a table, like a wall that we can connect this to. And we've got a couple of dimensions to work with. We know that our total string length is 3.7 meters, but we know that the distance between the wall and the pulley is 3.0 meters. This is 3.0 meters from here to here. That means this has got to be 0.70 meters from here to here, so that the total length is 3.7. We know that the mass is 5.0 grams, and we're trying to figure out how long it takes for a pulse that is generated near the wall to reach the pulley. We're not yet concerned with what happens to the pulse after it reaches the pulley. We're just concerned with the first part of this interaction. So let's take stock of what we know. So the mass of the string is 5 grams. We're going to need that in kilograms. So let's make that 5.0 times 10 to the negative 3 kilograms. The string length, let's call this L total. That's 3.7 meters. And I'm going to say that this 3.0 meters is something I'm going to call L1. 0.70 meters, I'm going to call this L2. So that's equal to L1 plus L2. I know that there's a certain amount of mass that is connected to this string. So I also know what the free body diagram should look like for that suspended mass. I have string tension pointing up, and I'm going to say W sus for the weight of that suspended mass pointing down. And F net in the Y direction is going to be 0 because that mass is not accelerating. So I know that TS has the same magnitude as W sus, the suspended weight. The suspended weight is just going to be M suspended times free fall acceleration. So we can calculate the tension in the string outright. So let me grab a calculator and we can do just that. Or actually, we've got a 500 gram mass. So I'll add this up here. M suspended is going to be 0.500 kilograms. So that means that M suspended down here is 0.5 kilogram, and we're going to use the 3 sig fig version of free fall acceleration. So 9.80 meters per second squared. This is going to be equal to 4.90. Let me make that legible. 4.90 newtons for the string tension. So that is part of what I need to figure out the wave speed. The next piece is going to involve the linear density. So let's make that blue. Our linear density mu is going to be the mass of the string divided by L total. this is 5.0 times 10 to the negative 3 kilograms divided by the full 3.7 meters. And let's see. We're going to end up with a linear density of approximately 1.35 times 10 to the negative 3 kilograms per meter. It's not going to break down any more nicely than that. But we have now this tension that we can combine with mu. So we make some space down here. The speed of a wave on this string is going to be the square root of the string tension divided by mu. So the square root of 4.90 newtons divided by 1.35 times 10 to the negative 3 kilograms per meter. We can take a look at the units in a moment. So under that radical, we're going to get 3,626. I'm going to just round to the nearest whole number here. And I've got newtons divided by kilograms over meters. So let me write this out a little more nicely. We know that a newton is a kilogram times meter over second squared. So newtons over kilogram meters is just this. I lose the kilograms here. I've got meter squared over second squared. When I take the square root, that's going to give me exactly the unit that I'm expecting. So let's take that square root. This is going to be 60.216 meters per second, and we'll worry about sig figs later. So the question that we're trying to answer is not simply how fast does this wave propagate, but how long will it take for a pulse to travel from the wall to the pulley? So we're going to take that wave speed and connect it to this definition of speed from semester 1. So we have a distance that the pulse has to travel divided by a time interval. That time interval is what we're trying to actually figure out. And in our terms, the labels are the names that we used for this. The distance that the pulse is going to travel is L1. And then delta T is going to be the time it takes to travel that distance. This is going to be the same as the string that we just calculated. So if we solve this for delta T is going to be L1 divided by V substring. L1 is only 3.0 meters. However, the entire string's mass is what we were given, so we had to consider the entire 3.7 meters to get the appropriate linear density. And let's bring this here. So we have in the denominator 60.216 meters per second. We have a distance divided by a speed. That's going to leave us with a time. And let's see what we get here. That ratio is going, or that value is going to be 0.0498 seconds. And we have, I believe, yeah, 2 sig figs to work with. This will be 0.050 seconds for delta T. Okay. So does anyone need to see or hear any part of that one more time? If not, I'm going to stop sharing on this end so I can go back to these notes. There we go. Okay, so we've just determined how long it would take for a pulse to travel the 3 meters distance on this string here. Now, to build off of this a little bit, or to kind of really tie us back to something I mentioned earlier, we have to develop a completely new model to deal with waves because the disturbance that we're talking about is one that happens both in like space and time, same time. So waves are not localized the same way that the cars that we used to make motion diagrams way back when in semester 1 were. So the particle model fails. We've got to come up with a different method. And we can lean on something that we talked about in semester 1 when we discussed simple harmonic oscillations in chapter 14, I want to say that was, but um, the one that's called oscillations. We found that for an oscillator, like a mass on a spring or even a pendulum that was connected to, or just a mass connected to a string, that it was kind of easy to understand how the energy changed for a system like that, but it was a little bit more complicated if we wanted to come up with a kinematic equation, because the force that, let's say, a spring is exerting on a block changes with position. So in other words, when the spring is really compressed, the force that it's going to exert on the block is going to be a lot stronger than the force it exerts when the spring is only a little bit compressed, or if it's a little bit extended. So the kinematic equations were a bit different than what we encountered in Unit 1 of Semester 1. This is the conclusion that we reached when we were talking about simple harmonic oscillations. For an oscillator that had some angular frequency omega in radian per second and some amplitude capital A that just represents the maximum displacement either above or below the the x-axis or whatever your equilibrium position is. We could write these time-dependent functions so that the position as a function of time depended on the amplitude and the cosine of this quantity inside the parentheses. So omega t plus phi naught, where phi naught was just the phase constant. We take a derivative, that'll give us our velocity function. Take one more derivative, this gives us our acceleration function. So this logic is something that we can also apply to the situation that we see here. Now to backtrack just a bit, because I want to take a look at these 2 bullet points here. So the wave itself is not something that we can localize in either time or space. The flip side of that is the statement here. So one particle can only be at one place at one point in time. So we have to have some way to kind of go back and forth between what the particle model can tell us and what it can't. And what it can't is what the wave model is going to pick up. So we have a couple of different ways that we can evaluate a wave that's not localized in space or time. One, we can take a snapshot, which is exactly what it sounds like. Imagine that your lab partner is generating a wave and you take a picture on your phone. What you would see is an image of what that medium looked like just at that one point in time. So there would be no delta t because it's a still picture, but you would be able to see what the change in position would be for, let's say, this rope relative to its equilibrium position, where that equilibrium would just be coincident with the x-axis. And for this spring, the equilibrium positions of the coils are indicated by these dotted lines, so that you can see when the coils are further apart than normal, when they're closer together, and then when they are at their equilibrium position. So like these points here, the last 3 dots on the right-hand side of our snapshot graph for the spring represent parts of the spring that are just waiting for the disturbance to go through it. The ones that are on the left end are the ones that have the coils that have already gone back to equilibrium because the coil has been through them, or the, excuse me, not the coil, but the pulse has been through them. And then you've got this section here where all of these particles are grouped closer together than they normally would be. So our flip side, if instead we are not concerned with taking a snapshot that shows us what the entire rope or what the entire spring looks like at this one instant in time, if you were to just pay attention to one section of the string or spring and you take a video, then what you would have is a history graph because you are not focusing on the entire portion of the medium. You're looking at one spot and seeing how it changes its position from T initial to T final. And that is something that we can kind of put together by imagining that you just take a bunch of snapshot graphs and then you kind of line them up in time. And that's what is being indicated here. This is the case for the wave on a string again, where we've got our slightly asymmetric wave here, just so that we can tell the difference between the trailing edge and the leading edge. That's really the only reason why this is shown asymmetrically. It's not impossible for you to make a symmetric wave like this at all. So here's your snapshot at T1. You're just looking at this one point on the rope. Imagine there's a drop of paint on the rope and you're just filming what that drop of paint does. Then if you take your slides from T1, 2, 3, and 4, what you are kind of watching is the disturbance pass through just that one section of the rope. So if you lined all of these up together, because the x-axis is the same for all of these, and then you are just lining them up from earliest time to latest time, you would kind of get to see how that pulse travels through time, or not, that's probably a bad choice of words. You can see how that one section of string behaves over time. It's a bit more complicated when we are trying to sketch a history graph for the coil. So the concept is exactly the same. Your lab partner is generating a longitudinal wave on the coil. You take a bunch of snapshots and you can compare where each one of the coils is at T1, 2, and 3 with respect to where they were when the coil, or excuse me, when the spring was just stationary. So you've got a section here where there's no displacement between the current position of the coils and where they would be at equilibrium. You've got a point here where the spacing is greater than it would be if the coil were just at rest. You've got now a spacing that's smaller than it would be if the coil was at rest. Then it stretches out a bit more and it goes back to equilibrium. So you have a section here where your slope value, or not your slope value, but your delta x values are 0. Then as the coils spread out, your delta x values get larger. They don't get larger forever though, because your lab partner who is generating the wave isn't only moving their hand forward or only moving their hand backward, but they are consistently producing a wave or a pulse that is propagating. So these values will become more positive, but then we can count on them going back down to 0. So at 4 centimeters here, this would coincide with the center, or like the midpoint of this compressed portion of the spring. We're going to continue down here where now the displacement is, it's increasing its magnitude, but it's a negative because you can kind of relate this to the way that you would have to hold a ruler if you wanted to measure the spacing between, let's say, these 2 dots that I'm pointing to with my cursor and dots that are on the opposite side of the compressed part of the wave pulse. Think about the restoring force that is just inherent in a spring like this. The spring is always trying to set itself back to equilibrium. And if you think back to our discussion of Hooke's law from way back when, if you were going to, let's say, squish one end of a spring inward, the restoring force is going to be the one that resists your hand. And something similar is happening here, where now the restoring force that's acting on this part of the spring is one that wants to kind of yank it toward the left. So you have these negative values, or these values that are becoming more negative. They max out here, but just as we saw previously, there is an inflection point here where now we get back to our or like zero, or delta x being equal to zero. In other words, these are the parts of the spring that are still relaxed. They haven't received the pulse yet. So delta x is going to be equal to zero for those. Okay, so we have a thought question here. Let me pull this out of the way. So we have a picture up here at the top. This is a history graph. We know that because it is it's giving us information about an interval of time, delta t, not just one point in time like our snapshot graphs show. So if you were looking at just one section of string and your lab partner was generating a wave, that one section of string would be at equilibrium for the first 4 seconds. It would go up to positive 1 centimeter for delta y. It would stay there for 2 seconds, then drop back down and go to 0. So this is what's happening at x is equal to 4 meters on the string. We want to use this history graph to gain some insight about what the far left end of the string looks like. So instead of x is equal to 4, x is equal to 0 meters. Take a second to see if you can rationalize which one of these is correct, and then we'll talk it through like usual. So the speed of the wave is relevant here. Okay, this wave propagates to the right at 2 meters per second. So we're going to call that positive 2 meters per second. We are trying to use what we know about x is equal to positive 4 to make some judgments about x is equal to 0. So the delta x here is going to have a magnitude of 4. So 4 meters minus 0. Now, since the wave is propagating toward the left and we're trying to make some judgments about what's going on, the wave is propagating toward the right, we're trying to make some judgments about what the left side of the string is looking for, or what the left side of the string is looking like. We can take this delta x and our 2 meters per second and take that ratio. So 4 meters divided by 2 meters per second is going to give us 2 seconds. So in other words, if we take our original history graph and take that shape and shift it back 2 seconds in time, that will tell us what was going on at x is equal to 0. So on that basis, we can get rid of D, because this is something that's happened, or this is describing a further part of the string, so one that's further away from your lab partner's hand who's generating it. D wouldn't make sense in that context. C wouldn't make sense because x is equal to 4 and x is equal to 0 are not going to look exactly the same. So we're down to A or B. And here's where we would want to use that ratio. Just take 4 meters divided by 2 meters per second. We have a time of 2 seconds, and then shift it backward because we're trying to gain some knowledge about what's happening on the left side of the string. Not like we were asking about x is equal to 8 meters, but instead x is equal to 2 meters. And we get graph B here. And we know that A is not correct because, or let me phrase it this way, A would be correct if the wave were propagating more slowly. If it was 1 meter per second, then the ratio that we would get for delta t, we would take 4 meters divided by 1 meter per second. So we would shift 4 seconds backward. in order to figure out what that section of the string would look like. But since we're dealing with a 2 meter per second wave speed, it is B. So this is the description of how this one section of the string behaves over this 12-second interval. Another way to think through this is that whatever happened to x is equal to 4 meters had to have happened to x is equal to 0 meters earlier, because our wave is propagating toward the right, and we're assuming that, like usual, our horizontal axis is going to increase toward the right. So we're looking for earlier times. We would need earlier times to describe what's happening to a section of the string that's further to the left. Does anybody need to hear any part of that one more time? Right? Interrupt me at any time if you've got questions or concerns, either in chat or on the mic. So we saw a few slides back that we can lean on some of our logic from simple harmonic motion in semester 1 to understand essentially how we can incorporate both the variance in position and the variance in time, so that we can put them together and make one function that describes this wave. And what we're working toward is a displacement function. So the displacement axis that we see up here in each one of these graphs, we've got one history graph on the left because we're watching an interval of time delta t, and it's kind of describing what's happening to one section of our medium or one section of our string. And then on this side here on the right, we can treat this like a snapshot graph. It pertains to exactly one moment in time, and it's giving us an image of what this medium looks like over some displacement or some space delta x, as opposed to an interval of time delta t. So when we learned about amplitude way back in semester 1, we learned that amplitude is always something that we can treat as a positive. It's a magnitude, the same way that your height is always a positive, even if you're doing a handstand. So displacement is like the axis that we would use to measure that. You can have negative displacements, positive displacements, or zero displacements, but the amplitude is always going to be a positive value. So for this history graph of our sinusoidal wave, we can measure the amount of time that it takes for one complete cycle to propagate through this rope, or in other words, you can measure the amount of time that it takes for your one painted section of rope to go from equilibrium to its highest point, to its lowest point, and then back to equilibrium. That would be one complete cycle. And you can measure that from peak to peak or trough to trough as well. So this, again, is our reminder for why we need an S subscript for our string tensions, because we're dealing with now the period here, an interval of time. If we take a look at our snapshot graph, instead of measuring the amount of time separating adjacent peaks, you can measure the amount of distance separating adjacent peaks. And that would be a wavelength. And I believe this is our first time talking about wavelength. We talked about period and frequency back when in our simple harmonic motion discussion, but this is our first kind of time diving into the wave model. So think of the wavelength as measuring the same property of a wave that a period does, just in a spatial sense as opposed to a temporal one. So this wavelength lambda is something that's going to have units of meters or centimeters. It's a length, just like the name suggests. So we should be able to use what we know about the definition of speed, and specifically the definition of a period, capital T, to come up with another way that we can quantify the speed of a wave. So if we take a look at what's going on down here at the bottom, these are the same images again, but with some new text. We saw in our practice problem that the speed of a pulse that we imagine plucking on our stretched string and then letting it propagate from one direction to the next, that speed could be described as a distance over time. That's what speed is. It has to be something that we can boil down to something this basic. So the distance that this one pulse would travel can be, or I should say, really one cycle can travel. That is something that we can line up with the amount of time that it takes for that cycle to complete itself. So it's not just any old distance or any old time. It's not the length of the string in this context, but the length of one cycle divided by the time for one cycle. That should give us the wave speed. And here we just have lambda times the frequency. This is just a reminder that frequency and period are reciprocals of one another. So the ratio of lambda and t is going to be the same as the product of lambda and f. So we can build off of our last scenario and figure out what the wavelength and period would be for a 60 hertz wave traveling through the string from our previous example. So I'm going to switch here and then jump over to the tablet again. So that was example 1. Here's example 2. What are the wavelength and period of a 60 hertz wave traveling through the string from example 1? I'm going to start with the period. We know that period and frequency are reciprocals. So if we know what f is, 1 over that value is going to be the period. Remember, hertz is something that we can equate to either cycles per second, inverse seconds, so s to the 1 power, or 1 over s. Those are all interchangeable. So if I take 1 over 60 hertz, that's exactly the same as saying 1 over 60 inverse seconds. So 1/60th of a second. And 1/60th of a second is like 0.016 repeating. Let me double check. Yeah. Okay, so that's seconds. If we were going to apply sig figs here and we have 2 sig figs to work with, it's hard to tell, but we had 60 with a decimal point, so that's 2. We would round this to 0.017 seconds. For the period, that had nothing to do whatsoever with the speed that we calculated in part 1. So any 60 hertz frequency or any 60 hertz wave is going to have the same period regardless of what the wave speed is. So to say that another way, the thing that does change when you send a wave through different media, but it's 60 hertz both times, would be the shape of the wave. So in other words, what your snapshot graph would look like. So this one does not depend on the speed. Say of the wave, just to make this clear. The wavelength is going to depend on that wave speed. So let's go to b is equal to lambda over the period, which is another way of saying lambda times f. We have f, we have v from the previous question. So this means that lambda is going to be the ratio of v and f. And let's see. Our unrounded wave speed from the previous question was 60.216 meters per second divided by 60 hertz. We're going to get something that will round to 1, but let's look at our exact value. This is 1.004 meters, but to 2 sig figs, this is just 1.0 meter. Okay, any questions before I jump back over to the main notes? Okay, let's quit sharing here. Pick up again there. So we have a wavelength of about 1 meter, a period of 0.017 seconds. Now, our goal here is to come up with some way that we can express the variance in position and time together in one function. So the way that we can do that is by developing a displacement function from a snapshot graph. So remember, the snapshot graph is the one that applies to just one moment in time. It tells you what the string or the whatever medium you're working with, it tells you what that medium looks like at that one point in time. So we've got our displacement where our bounds here, or our max and our min, would be whatever positive amplitude is and whatever negative amplitude is, where this negative A is just a marker. It's just a value on this displacement axis. The amplitude is always going to be treated as a positive. And I've got a snapshot of this wave where at t is equal to 0 and x is equal to 0, the wave is neither at its minimum displacement nor at one of its maxima. So in other words, I caught it in between. I didn't catch it when the displacement was equal to either positive A, negative A, or 0, but somewhere in between. And it turns out that's fine, because I know that if I were to try to define the amount of space in between this this peak and the next peak, they're going to be different by just one unit of lambda, whatever lambda is. And we don't have enough information to determine what lambda is just by looking at this graph, because we don't have any units on either axis and we don't know how quickly this wave is propagating. What we do know is that this is a periodic function, so that if I were just to add another lambda, I would find another peak and so on. So my general or my basic displacement function is going to look like this up here at the top. I'm starting with a snapshot graph. So my t is going to be equal to 0 regardless, but I can express, or I can kind of quantify how the value of x changes based on the rest of the stuff that's on the right-hand side of this equation. So the amplitude is going to stay the same as long as your lab partner is moving their hand up and down the same distance. It really doesn't depend on whether they're traveling at a fast speed or a slow speed, just that A is consistent. And because this is repeatable, we can use sine, and we can take 2 pi times this unit x over lambda. Add that to our phase constant, phi naught. That's going to be non-zero in this case, because we're starting kind of somewhere in between a min and a max. And we know that since this is a periodic function, if I were to write an expression for the displacement at x plus lambda, then the only thing that would change is that the numerator of this expression here would be an x plus lambda instead of just an x, where this x plus lambda, that ratio is going to be unitless. So I would just have 2 pi radian plus however many radian for the value of phi naught. Let's expand that outward. We've got a sine 2 pi times x over lambda plus my original phase constant phi naught plus 2 pi. So in other words, I have something that I can basically kind of group back as words. What do they do? I can take these two pies and put them together. I end up with exactly the same expression as we had before. So that's not a shock. We knew that this was something that was periodic, but now we found how we can express like this d as a function of x. So to say that another way, we've kind of taken this from a single snapshot graph and kind of unstuck it in time. We know what d as a function of x is going to be for any t that we might want to plug in. So this expression up here at the top right is just a repeat of the last thing that we saw on the bottom of the previous slide. But even though we don't know what this wave speed is, we know that if v is equal to x over t, then the distance that this wave is going to move in some interval time t is going to be v times t. Like distance is equal to rate times time from way back when. So because this wave is propagating toward the right, and this is a sign convention that we're going to run into here, if I wanted to determine what the displacement would be for not just x plus lambda, but x minus vt, and I expanded it outward like I did before, I would have an x over lambda. We know what to do with that because that was our first step in the previous slide. And I would have this v times t over lambda term that showed up inside these square brackets. We know that v over lambda is just going to be the frequency, and frequency is 1 over the period. So that all the green text goes together. And I believe, yeah, so now this one at the top of the page is a repeat of the bottom of the last statement from the bottom. I can go back to the definition of angular frequency from semester 1. That's the omega that we saw earlier when we were talking about our simple harmonic motion equations. We also saw that omega could be it could be an angular speed depending on like the context of the problem that we were working on. The point here is that omega is going to be equal to 2 pi over the period. And we just uncovered the fact that v over lambda is equal to 1 over the period. So we can draw a relationship between frequency, period, this 2 pi, and a wave number k that we're introducing, where k is just going to take the place of the 2 pi over lambda. Unfortunately, this is another k. K gets used quite a bit, and we're using it for a different quantity here. This is something that we would just measure in radian per meter because the 2 pi is in radian and our lambda is a length. The point here is that we can take our 2 pi times x over lambda and then replace that the 1 over lambda with this k over 2 pi. That's what's happening here. So I've got k over 2 pi there, and then an omega over 2 pi, because I'm incorporating this expression on the right-hand side as well. So I'm trying to get rid of that 1 over period, in other words. And what I end up with is this expression here. I can cancel out these 2 pi's that show up in the denominator with the one that shows up inside or right ahead of the square brackets. And I've got displacement as a function of x and t. So I've kind of unstuck it in time. I started off with a snapshot graph. I unstuck it in time. I've got the amplitude times the sine of this product k times x minus omega t plus phi naught. And this negative sign here is a consequence of the fact that we either knew or assumed. Let me go back and look at our notes. Yeah, so we just made the assumption that the snapshot graph depicted a wave that was traveling toward the right. As a result, there's a negative sign here inside of the sine function. But if instead we had a leftward propagating wave, we would replace this with a plus sign. But this is our general expression for the displacement of any wave. And we are getting down to our last couple of minutes here, but we can start with example number 3 at the beginning of our next lecture. So here we have another snapshot graph. This depicts what's going on at t is equal to 0. This is a wave on a string that's traveling toward the left at a known speed. We didn't have a known speed beforehand, so we weren't able to, if I backtrack a little bit, we weren't able to determine what k is or what omega is. And if I go back a little bit, yeah, we didn't have numbers on our y-axis either. So we knew that capital A was the amplitude, but we couldn't find a number to it. With this graph here at example 3, we do have labeled axes. We do have a speed and a direction. We can write a displacement function that includes a numerical value for A, a numerical value for K and omega. We can figure out what the phase constant is. We would know everything except for our two variables, X and T. So we can start with this because this will take a little bit more, well, a lot more time than we have left. We have just a few kind of seconds at this point here. So I will stop sharing here and let me log out over here. I can control the recording again. Okay, so do we have any questions or concerns before we call it a day for this morning?